Good evening, everyone. So, I welcome you all to week 9 for the problem solving session on the course Computational Fluid Dynamics by Professor Sreenivas Jayanti from IIT Madras. So, this week we are seeing the problems from the week 9 course and we'll see how to solve them. We'll just wait a minute before we are starting with the session. So, yeah, we'll resume the session now. So this in last week we solved the methods to solve the Navier-Stokes equation for both compressible and incompressible fluid flows in the system. So this week it was mainly focusing on numerical methods used in the CFD problems. So we'll just start with the session. The first few problems are the practice problems given in this, followed by the next few problems covering the assignment problems. So these first few are non-graded practice problems given in the NPTEL course for the week 9. So now we'll start with the session. In this it is given that you wish this is a case followed by questions from the case. So the case is basically you wish to solve the Poisson equation in a two-dimensional domain spanning a length L in the x direction and width W in the y direction. You have divided the length L into 20 equal intervals and width into 30 intervals. You have non-zero Dirichlet flow, Dirichlet boundary conditions on all sides. You discretize the Poisson equation using central difference scheme of second order accuracy. The source term is a constant. You wish to solve the resulting set of linear algebraic equations which you have expressed in matrix form as Ax is equal to Q. For this problem, answer the following questions. So the question is basically we have a two-dimensional domain like this, considering this to be length L and this is width W. So basically this L length is divided into 20 equal divisions, somewhat like 20 divisions, and this W is divided into 30 divisions, and the boundary conditions are given. This boundary conditions are given to be Dirichlet boundary conditions What is Dirichlet boundary conditions? It is when we are specifying the values at the boundary, that is known as Dirichlet boundary condition. On the other hand, we have one more thing, that is Newman boundary conditions, where we specify the value of flux or we specify the values for the derivatives. So in this it is given all the boundary conditions or Dirichlet, non-zero Dirichlet boundary conditions, and we are solving for Poisson equations in two-dimensional domain. And it is given that source term is a constant. You wish to solve the resulting set of linear algebraic equations which you have expressed in the matrix form as Ax is equal to Q. And we are using central difference approximation of second order. So moving on to the problem, what we have in this, we'll answer the following questions. These are the things that are given in this problem. The first question is, which of the following equations is an appropriate governing equation for this problem? Dou f by dou t plus a dou f by dou x plus b dou f by dou y is equal to 0, where a b is greater than z. A and b both are greater than 0. Second one is dou f by dou t is equal to gamma times dou square f by dou x square plus dou square f by dou y square is plus c, where c is greater than or equal to 0. And third one, it is gamma times dou square f by dou x square plus dou square f by dou y square plus d is equal to 0, where gamma and d are both greater than 0. And finally, it is gamma times dou square f by dou x square plus dou square f by dou y square plus e is equal to 0, where gamma is greater than 0 and e is less than 0. The difference between both these equations is d is greater than 0 here, e is less than 0 here. So we know the answer to be these two, 3 and 4. In option 1 it is given 1, 1 and 2, or 4 is right, but along with that 3 is also right. So the answer to this is 3 and 4. We will see how this is in the next slide. Basically the Poisson equation is given by this, where dou square f by dou x square plus dou square f by dou y square plus dou square phi by dou z square is equal to some function of x, y and z. In this problem it is given this to be a constant. Source term is given as constant. So the answer is obviously option 3 and 4. Plus d is equal to 0 or plus e is equal to 0. Since this is a constant, it does not matter that much. And we are dealing with the two-dimensional flow. So both 3 and 4, both options are right. In the sense that, 3 and 4 are both right for Poisson equations. We have dou square f by dou x square, dou square f by dou y square plus some constant. Here the same way, dou square f by dou x square plus dou square f by dou y square plus e is equal to 0. The main thing is gamma is greater than 0. That is the point to be noted here. D and E can be greater than or less than 0. That doesn't matter because it is given as constant. So now we'll move on to question number 2. Poisson equation is an example of hyperbolic equation, parabolic equation, elliptic equation. It is of mixed character. In the last slide itself, we have seen that Poisson equation is given by this, where it is also mentioned that it is an elliptic partial differential equation. So the answer is elliptic equation. This one we have seen before few classes how the equations are classified as hyperbolic, parabolic and elliptic. Based on this, how the boundary conditions needs to be specified for that specific problem. So Poisson equation is an example of elliptic equation. So now we'll move on to question 3. For an interior point, how many terms involving f, I, j will have non-zero coefficient values in the discretized equation? So basically we are solving for the Poisson equation. It is given by this equation, dou square f by dou x square plus dou square f by dou y square is equal to c. That is some constant. It is given that we are using central difference scheme. uh, to discretize this equation in the specific problem. So when we are using central difference scheme, we will be getting these terms. That is, for f we will be using I minus 1 f keeping j constant minus 2f ij plus f I plus 1 j divided by delta x square. Similarly, here we are keeping j constant, whereas when we are going for y derivative, we will be having I constant. I is constant here and j is varying from j minus 1, j and j plus 1. Here if we are considering this to be I comma, we will consider this is I comma, okay, this one is j, this is j minus 1, this is j plus 1 and j plus 2 and this is j minus 2 and this is I plus 1, this is I plus 2 and this is similarly it is I minus 1, this is I minus 2. When we are dealing with this, we'll for an interior point, it is to be noted, it is interior point, not boundary condition. Boundary condition means some coefficient would become 0. Since not 0, it would be having certain values because it is given that they are non-zero values for with Dirichlet boundary conditions. So how many terms involving Fij will have non-zero coefficient values? So it is, this term would be there, and Fi minus 1 comma j, this term would be there, I plus 1 comma j, this term would again be there, and this is Ij minus 1, Ij and Ij plus 1. So when we are dealing with the discretized equation, we will be dealing with 5 points when we are dealing in the interior points, not boundary condition. So the answer to this is 5, not 3, not 7. The answer is 5. So now we'll move on to the next question. The number of equations to be solved will be when we are solving for the Poisson equation. In this it is given that dou square f by dou x square plus dou square f by dou y square is equal to c. So obviously we are having one discretized equation for this. When we are dealing, this is for when we are dealing at the point I comma j. So the number of equations would be depending on the number of points, number of grid locations. So consider a smaller grid. This one is pretty large. So this one is fine. So here in the question it is given that in the x there are 20 divisions and in the y there are 30 divisions, right? So here consider this problem, this smaller scale. We are having 4 divisions or 4 cells in the x direction and similarly 4 cells in the y directions. So how many points do we have? This is 1, this is 1, this is 1, this is 1. This one is a boundary point, so it is not valid when we are doing this. And again we have one more point, one more point, one more grid point, one more grid point, one more grid point, one more grid point. In all these grid points, we would be solving the equation. So all these points you would be solving the equation. So the number of equations to be solved depends on the number of grid points, right? Number of grid points. Grid. More specifically interior grid points. So here for 4 cross 4 we are having 9 points, right? 9 points. So obviously if there are 4 cells, we are having 1, 2, 3 grid points, right? For 4 cells we are having 3 grid points. Similarly in 4 cells we are having 3 grid points. So it is, if there are n cells, we have n minus 1 grid points. So for n cells, we have n minus 1 grid points, interior grid points. And n minus 1 number of equations need to be solved. Right. So for this problem, we would be having 30 cross 20. When we are putting it in the equation, when we are putting it in the, these many cells we have, right? 600 cells we have. So the number of grid points, interior grid points that we are having would be 29 cross 19. So 29 cross 19 is 551. So the number of equations needs to be solved is 551. So answer to this is around 550. Right. It is not 600 because we are leaving out the boundary points, and so the number is actually less. Actual number of grid points in the cell would be like n plus 1. That is, if there are 20, 21 and 31 would be there. From this itself we could see that 1, 2, 3, 4, 5. 5 points are there in the x direction and 5 points are there in the y direction. And similarly, but we are leaving out the boundaries, so it is like n plus 1 points, grid points would be there, but leaving out the two boundaries, we would be having n plus 1 minus 2 or n minus 1, both are same. Like n cells, we would be having n minus 1 grid points or interior grid points. I remember similar question we have also solved in the assignment 1 or assignment 2, somewhere near that, asking for the number of grid points or something. Yeah. Coming back, the number of equations to be solved will be 29 cross 19 or 19 cross 21. That would be 551. So it is around 550 equations need to be solved. I hope this is clear. If any one of you has any doubt, please feel free to ask or put it in chat box. Yeah. Now we'll move on to question 5. The percentage of elements in the coefficient matrix A having non-zero value will be of the order of greater than 99 percentage, it is less than 0.01 percentage, and 1 percentage, and 50 percentage, and it is 1 percentage. So we'll just see how to do this. So yeah, the thing we are doing when we are dealing with these problems is that we are first taking the original Poisson equation, and since we are using the central difference scheme, we are writing it out in the discretized form as this. Now we'll just do a simplification of this for our better understanding. Right. Okay, like we are having this cell. Mm, consider this, we are having a smaller cell. For calculation purpose, we keep it like this. So for calculation, we'll just have a smaller grid for our better understanding. In this, we are having two cells in the x direction and three cells in the y direction, right? So when we are using this, we'll have it as 0, 1, 2, and 1, 2, and 3. So when we are you putting this in this discretized equation form, uh, once again, just wait. Yeah, I could not hear you. Can you just say a little louder? Okay, we'll just start the session. Okay, now for this, we'll just have a smaller grid for our understanding. So in this, we are having 0, 1, 2, 3, and similarly we have 1, 2, and 3, right? So we will be writing equation for this point and this point and this point and this point. So we will be having four equations. This was what we saw in last section also. We have three cells in the x and three cells in the y. So the number of equations that we are going to solve is 3 minus 1 cross 3 minus 1, that is 2 cross 2, it is 4. So we'll be writing equations for this and this and this. So if we are writing equation for the point f1 comma 1, what we would be having is f I minus 1 is 0, 1, yeah, minus 2f 1 1 plus f 1 plus 1, it is 2 1, divided by delta x square plus f 1 0 minus 2f11 plus f12 divided by delta y square equal to some constant. So this is for f1 comma 1. Similarly, I guess okay. Similarly, if we write it for f21, okay, f21, what we would be getting is f. This would be f1 1 minus 2f 21 plus f 3 1 by delta x square plus f this would be 2 1 minus 1 0 minus 2 times of f21 plus f2 2 divided by delta y square is equal to constant. So what we would be getting is we have certain known values, right? For example, in this 0 1 is a boundary point. So 0 1 we know, f11 is unknown, f21 is again unknown, and f1 comma 0 is again we know because that is a boundary point. And similarly minus this one also is unknown, and f1 comma 2 is unknown. So one equation we have 4 unknowns because these would be solved from this equation. Others are like boundary points, so we know the values at the boundaries. So similarly we should be writing for f12. So this would be f02 minus 2f12 plus f22 divided by delta x square plus f okay it is we are writing for 1 2, right? So it is 1 2 minus 1 is 1, yeah. So minus 2f12 plus f13 by delta y square is equal to constant. So similarly we should be writing for f22 also, and we would get one more equation. So when we are putting all these equations in the matrix form, that is Ax is equal to B form, all the constants would go in this right hand side matrix, and in x we would be having 4 points like f11, so f12 and f22 and f21. So we would be having it as f11 f12 f21 and f22. These would be the points. And in A matrix, that is the coefficient matrix, what we would be having is basically all these values put together, we would be having it as 1 1 and 2. Yeah, it would be minus 2 times 1 by delta x square plus 1 by delta y square, and this would be 1 by delta y square, and this would not be having, and similarly 1 by delta y square, and this would again the diagonal element would be minus 2 by 1 by delta x square plus 1 by delta y square, and this last element would be 1 by delta x square. And diagonal element is common in this, and here it is again 1 by delta x square and 1 by delta y square. One element is 0. These are all 0 elements, like 0 0. I mean this is for this specific problem, and again we would be having this as 1 by delta x square. I mean when we are putting all these equations in the matrix form, we would be having a one matrix. So in that matrix, what similarity we can observe is that the diagonal elements are remaining as non-zero. So I'll just discard the ink alone. Um, so yeah, in that matrix, what was observed is that diagonal elements were observed to be non-zero. So in this specific problem, what we would be having is that number of equations, to be solved is we would be having 551 equations, right? Number of equations to be solved is equal to 551, and the total number of elements in matrix coefficient matrix A would be number of elements in coefficient matrix A is equal to 551 cross 551. That would be around 1 into 551. Okay, that is around 33601, and these many equations we have. So since there is a diagonal element present in all these cells, if we ignore the boundary, we should be having the number of diagonal elements present, we should know, right? And along with that, we could we can form a pattern. There are certain cells in which we had both delta x square fraction and delta y square fraction, and in remaining we either had one. So based on that, the total number of uh, equations in which we were able to find out that x fraction and y fraction, that is from the previous thing, like if we put to, like we just took a smaller matrix, right? In that it was observable that diagonal elements were present in everything, and along with that few other elements were also present. So we would be having 551 equations. In those 551 equations, if we would be having it as 551 cross 551. So if we are separating the equations and having some common pattern to observe it, like just a minute. In which everything would be present, like since this is a two-dimensional case, in few this is the discretized form of the equation, right? So in some equations we would be having this coefficient, this is put together, this is 5, but like two are the same, so we would be having 5 factors in certain equations. So we need to find the number of those equations. Those equations would be so we should be ignoring the boundary points. Simply to put, when we are ignoring the boundaries, we would, how many equations would we be having? It is 3, right? And also we should, like in the boundary points, we would not be having we would know the values. And also if we take the the grid next to the immediate boundary, we would then be knowing the number, one boundary conditions would be coming into picture in those equations. So basically what I'm trying to say is, these boundary points we know, like this entire outer boundary we know. The next boundary is this one. In solving these equations, we would be either use, if consider if we are taking this point, right, we would be having this many grid points. So this is comes as boundary and this comes as boundary. And similarly for this again, this point also included. Uh, those boundary points would come into picture. So we are taking the interior points alone. Those interior points would be having pi coefficients. So how to take the interior fractions? So we are like the interior grid points alone are like 29 cross 19. So the interior points alone were like 20 interior grid points were like 29 cross 19, right? So again we are subtracting 2 more from that. So it would be 29 minus 2 and this is 19 minus 2. So this would be giving us 459. Once again, let's just confirm. 27 cross 27 cross 70. Yeah, this would give us 459 grid points. In those 459 grid points, if we write the equations, we would be having 5 coefficients in those equations. So this would give us 459 into 5, that is 2295. This 2295 comes from that. And we are having a boundary points where we have one, I mean we, okay, we'll take this bound, I mean this line, that is the grid immediately next to the boundary. So in those things, okay, we'll take the go with the x boundary first. I mean not boundary, the grid immediately next to the bottom. The line, the grid points next to the bottom wall. In those things we would be having one x value would go as boundary conditions and we would be having the remaining points. In this we are not taking the cornermost points, other things we are taking. So basically we would be having a similar thing, 27 29 minus, oh sorry, it is 29, okay, it is 19, 19 minus 2 cross 4 we would be having. So that is like 136. I mean this would be next to the bottom and the top wall. We can put together both the walls. So it would be 19 minus 2 into 4 into 2. And similarly, if we consider the grid points next to the left and right wall, we would be having it is 29 minus 2 into 4 into 2. That would give us 2. So this is 216 and we have excluded the 4 corner points, right? That's those that were sharing the boundary walls. So when we are including those points, that 4 corner points are left. The corner grid points, in those how many points would be there? There are 4 points and in those we have one diagonal point would be there, that is the concerned point, and the remaining one from the x and one from the y would be known. So one unknown in y and one unknown in x would be remaining. So we would be having 3. So this put together we would be having 12. So these are all the grid points that are remaining unknown, or we can say, I mean not unknown, they are remaining as 0. non-zero, non-zero. So these, when 2295, 216 plus 136 plus 12, these are the non-zero grid points in this specific problem, and the total number of equations to be solved is 551, and the number of grid points total is 551 cross 551. I mean number of elements in the matrix A. So when we are dividing this by this, we would be getting it as 0.8 percentage. So the answer to this problem, it is around 1 percentage. It is not greater than 99 percentage or not less than 0.01 percentage. It is around 1 percentage. So that is the right answer. So it is answer is 0.8 percentage. So the answer is around 1 percentage of the coefficient matrix would be having non-zero values. So yeah, I hope this is clear. Now we'll just move on to the assignment week 9 assignment problems, and we'll solve the problems. So in this it is given that these are the assignment problems, 10 questions. These in the coming up slides. So in week 9 assignment, it is question asked is, you wish to solve the Laplace equations in a three-dimensional domain spanning a length L in the x direction with W in the y direction and height h in the z direction. You have divided the length L into 40 equal lengths with W into 30 equal intervals and height h into 25 equal intervals. You have Dirichlet boundary condition on all sides. You discretize the Laplace equation using central difference approximation. You wish to solve the resulting set of linear algebraic equations which you have expressed in the matrix form as Ax is equal to Q with lexicographic ordering of equations. For this problem, answer the following questions. So it is given that we have a three-dimensional domain. Here it is length L and with W, I mean it is height h in the z direction with W. So it is X, Z and Y. So L domain is divided into 40 grid equal intervals, and width is divided into 30 equal intervals, and height is divided into 25 equal intervals. So we are discretizing the Laplace equation using central difference approximation. You wish to solve the resulting set of linear algebraic equations which you have expressed in Ax is equal to Q. So the Laplace equation is given by this, where del square phi is equal to dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square. In Poisson equations, it was equal to some specific values depending on the problem, whereas in Laplace equations that is becoming 0. So the Laplace equation is dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to 0. So we are discretizing this equation using central difference scheme, and we are rearranging them in the matrix form as Ax is equal to Q. And for this problem, the following questions need to be answered. So moving on to the problem, which of the following is true about matrix A? It will have 9 non-zero diagonals. More than 99.9% of elements of A will be 0. It will satisfy the conditions for strong form of diagonal dominance. So the options given are 1, 2, 3, all, or it is 2. I mean answer to this is 2. That is more than 99% of elements of A will be 0. This is right. We can't say about this. 9 non-zero diagonal is kind of impossible. It will satisfy condition form strong diagonal dominance. We should see how the equations are forming before answering. For this problems, this is a three-dimensional domain where we have a if we are discretizing something in the three dimensional, it looks kind of like this. So this is node, and yeah, the point is node, and this is boundary face, this is edge, this is cell. So moving on to the problem, we need to solve this. So okay, so in this we had how many equations? So in the last problem itself, we saw the number of equations to be solved for this for any problem. It was basically depending on the number of intervals in which it was divided. So in this problem it is 40, so it is 40 minus 1 into 30 minus 1 into 25 minus 1. Uh, this is 27,144 equations are coming. 9, yeah. So in this equations, we should first discretize this. So in the previous problem, we had a discretized equation for the Poisson. We just take this and we'll copy paste it and modify it accordingly. So this is the case for Poisson equation, but here we are using the we are using Laplace equation. So we'll use the Laplace equation, the two we are using in the three-dimensional domain. So this would become 0, and the number of equations would be, first we would be discretized in the I, like this one is discretized with respect to I mean x. So it is f I minus 1 comma j comma k. K also remains constant in this. So minus 2 f I j comma k plus f I plus 1 comma j comma k. And similarly it would be I comma j minus 1 comma k minus 2 f I j comma k plus f I j plus 1 comma k. And again this is 0. Since we are dealing in the three-dimensional domain, we have one more discretization thing. So it is here I and j remains constant. Sorry, I and j remains constant, and k would be varying from k minus 1 to k plus 1. This is, we are dealing with the central difference scheme. So for the second order, second central difference scheme, this is the formula. So and it is in z, or depends, k and j can vary depending on however we want. And so how many terms do we have in this? We have totally we have 9 terms, 9 coefficients, but since these are all common, we have 7 points in, I mean 7 coefficients in a single equation, right? So the number of equations, what was the question by the way? It was asking which of the following is true, and we said more than 99.9% of the elements of A will be 0. So yeah. We'll just find out the number of non-zero elements, and then we'll move on to number of zero. So in the similar problem that we solved in the Poisson equation in the last practice problem, we should find the number of interior grid points first of all. So number of interior points in this would be we have the, this is actually basically 40 minus 1, it is 39, oh sorry, 39 cross 29 cross 24 is equal to 0. Okay, equal to this one. So in this it would be 39 minus 2, because we are we are leaving out the two boundary extreme, leaving out the extreme interior, we can say it like for our convenience, where we are leaving out the nodes that are present immediately next to the boundary. Interior points, number of interior nodes, node points, uh, leaving out the nodes next to the boundary points, that would be 39 minus 2 into 29 minus 2 into what is 24 minus 2. What we would be getting is and this is basically equal to 24 7 7 so 49 3 24 472. Just a minute, I'll just check the calculation once. 39 into 29 into 24, it is 2711144. 37 into 27 into 22, or else the 40 minus 3, 37 into 30 minus 3 into 25 minus 3, this is 21,978, 21,978. So this one is 21,978 equations we would be having. And if we are like having the grid points immediately next to the okay, here what we would be doing is, in those we saw the grid points in the x and y, in the similar fashion we should be also solving it for the where was that, the grid points next to the bottom wall, left wall, and so everything. We'll just use it for our convenience, copy paste it. Don't see the values over here. Yeah, so since this is a three-dimensional problem, we would be having the bottom and the top wall. Next to the bottom and the top wall, we should be finding out the grid points or the node points, the number of that. So on putting that, we have it as we would have actually 2 2, and it is in those points. For example, if we are taking this immediate boundary, if it is, the boundary, the point immediately to this. So if it is the next to the bottom wall, we would be having the, how can we say it is, should be actually H, right? Yeah. So it would be bottom and the top wall, it would be it was the 25, right? And 25 25 minus 1 into 24 into 2 plus 2 plus, sorry, it is 2 plus 2 plus Okay, 2 plus 2 plus 1, 4 plus 5 plus 6 into 6. And similarly, left and right wall, it would be bottom, and then what we have in the next to the left and right, top and bottom, front and back, front and back. That would be 30 minus 1 into 6. Again this would be 40. 30 minus 1 into 6. Yeah, what we would be getting is that, one second, just a minute. 24 into 6. This would be 1. I mean, again, since we are dealing with two walls, it would be 2. Number of points into 2. So it would be 24 into 6 into 2. It is 288. It is 39 minus into 12, 468, and 29 into 12. It is 348. 348. So we have, and the left out are the corner node points would be having, how many points would be there? 1, 2, 1, 2, 3, 4. Similarly, 1, 2, 3, 4, 4. I mean, they would be sharing two. Okay. 1, 1, 1. 3 points they would be sharing. I mean, would be known from the boundary. So 3 would be unknown. And if we put together that 1, 2, 3, and 4, it would be 48. 4 4s are 3, 4. Yeah, we would be having 4 3s are 12. 1, 2, 3, 4, 5, 6, 7, 8. And again bottom 1, 2, 3. Here we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Nine, 10, 11, 12, 13, 14, 15, 16. So yeah, we'll be having 16, sorry, 12. It would be 4 into 4 into 3. So again this would come as 48 points. And again this is 221978 into we have 7, right? Yeah, 2197 into 7. 153846. 153846 plus 468 plus 348 plus 288 plus 48 divided by 27144. 27144 into 100 minus 100, 99.9. Okay, it is slight confusion. 21978 into 7 points would be having this equation. So this is 153846. So the answer we are getting is 0.021%. So finally we are having 0.99. I mean, these many non-zero elements would be there in the equation. And to the question basically was asking about was stating about the number of zero elements. So what we did is, first we calculated the interior innermost grid location, that is if we are considering this okay, this one is kind of smaller one. We'll have 1 2, okay, or else what we can do is we can eliminate this. Okay, here itself we will add one more we'll add one more grid location in this. So again here also, so the number of what we have done is we have taken only we have left out the grid location immediately next to the boundary. So this one is left out, this one is left out, I mean we have calculated separately, this one, this one, this one, this one, and this point is also. So this is the innermost points, and similarly we have left this one is a sort of boundary condition when we are dealing with the boundary phase when we are dealing in 3D. Similarly, we have this one is taken from this uh, edge or this boundary, I mean this grids, because we have left out this is boundary and this is inner interior grid next to the boundary. So this center one or the interior ones we have taken, that has come around 21978. In those points the number of unknowns would be from calculated, I mean number of non-zero coefficients would be from this. We are having 1 2 3 4 5, I mean this is 5 6 and 7 non-zero values, so we are multiplying by 7. We are calculating the number of interior grid points and multiplying by 7. And here what we are doing is, next we are calculating for the interior grids next to the boundary. In those things, the boundary is either shared by, I mean boundary values at the x is known, or the y is known, or the z is known. So here we are subtracting 1 from the 7th, because if we one point is known in the boundary condition, so 7 minus 1, it is 6 into two sides, that is top and bottom or front and back or left and right, and we are calculating the number of points in those, and we should find the corner grid points, that is like for example if this point we have not calculated, so this point what we know is, we know the x value and we know the, I mean we know the y value and the x value also. So two grid points, I mean two values are known from the boundaries. So it would be again 6 minus, I mean 7 would be the ideal one. So in the previous one value was shared, so we subtracted 1 from that, and in this we would be it would be shared between these, I mean if it is a cornermost we would be sharing it with x, y and z. So we have it as 7 minus 3, that would be 4. So how many grid points that we would be having is this, I mean not this one, 1 2 3 4 5, and similarly in this one 7 8 9 10, and that side 11 12. I mean imagine a cube, for example imagine a cube like this. This is, consider this as a cube, and so what we are dealing with this, the points in the corner. So I mean consider this is an interior cube. I mean these are the grid values immediately next to the grids. I mean next to the boundaries. So here how many values would be having? Here we have 1, 2, 3, 1, 2, 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, and again it would be 1, 2, 3, 4, 5, 6, 7, 8. I guess it would be 8, what I have written. It is 8 into 4, 32. That would be 8 into 4 is equal to 32. So basically 25 minus 24 plus 39 plus 29 plus 8 plus 2197978. Plus plus answer plus 24 plus 39 plus 29 2170. Okay, fine. It is like 8 4s are 32. It is 153,846 plus 468 plus 348 plus 288 plus 32 divided by 27,144 divided by 27,144 into 100.021, almost the same, so it doesn't change. So these many non-zero values, I mean 0.021 percentage of non-zero values are present in this system. So when calculating the number of percentage of zeros in A, it will be 100 minus this percentage, it is 99.97 percentage. So the answer is more than 99.9 percentage of elements of A will be 0. So the answer is right. I mean the statement which is right is more than 99 percentage of elements of A will be 0. So I hope this is clear. Now we'll move on to the next problem. Which of the following is true about matrix Q? So what is matrix Q in this is, it is given that we are writing it in the form of Ax is equal to Q. So it is Ax is equal to, in Q we are putting all the constants from the equations. So it was 144 in A equations that were solved. So Q would be a single matrix, row matrix, or I mean one column matrix with 144 rows and a single column. So it is a square matrix. This one is false. All of its elements have the same value. This is also false. All the elements are negative real numbers. This also we do not know. Basically they are just constants from these equations. So they can be anything depending on the things. So the answer to this is none. None of the above is true is the right answer. So I hope that is clear. Now we'll move on to the next two question. That is, the number of equations to be solved will be close to 27,000, close to 30,000, close to 33,000, less than 25,000. So in the previous thing itself we saw that how to solve the how to find the number of equations that needs to be solved. So it is we would be solving only for the interior grid points. So it is 40 minus 1, 30 minus 1, 25 minus 1, that is approximately it is coming as 27,144. So the answer is close to 27,000. So basically it is coming as 27,144. So the answer is close to 27,000. So how can we just visualize this as that? Okay. We'll just take a very small three-dimensional mesh. We'll divide everything into three. 1, 2, 1, 2. Similar for that, and here also we are dividing it as 1, 2, 1, 2. Similar to this. So the number of grid points in this would be, so the number of cells is 3 cells in X, 3 cells in Y, and 3 cells in the Z. So if we are imagining it, we would be solving in this points, right? In these points. So but not on the specific cell. It would be in the this grid and this, I mean this domain, this location and this location. So it is 4 points, but only in these two lines we will be solving, because this becomes boundary, this becomes boundary, and similarly this becomes boundary, this becomes boundary, this becomes boundary. So we are having 4 plus 4, one cell 4, one cell 4, it is 8. So we are having 2 minus 1 is, I mean 3 minus 1 is 2, and again 3 minus 1 is 2, again 3 minus 1 is 2, 2 2s are 4, 2s are 8. In that fashion we are getting it as 27,144. So the answer is closer to 27,000. It is not closer to 30,000. It is not close to 33. It is not close to 25. It is 27,144. So the answer to this problem is closer to 27,000. So this again is that in the coefficient matrix A, what percentage of number of rows will have the diagonal element to be equal in magnitude to the sum of the magnitudes of the off diagonal elements? Hmm. So it is 20. Okay, just a small thing. 40 minus 3 into 27 into 24. Actually, there is a small correction in this slide. Okay, we'll just go step by step manner. This is the discretized equation for the Laplace equation given in this problem. So what was, if we are putting everything together, what we would be having is that, I mean we'll just separate this out. Um, we'll separate it out. So when we are combining the Fij terms, what we would be getting is, okay, we have it for 1 delta x square, and we'll remove all other terms. It would be 1 in plus we would be having delta x square and by delta x square plus 1 by it will be delta y square plus okay what is 1 by delta y square and similarly plus 1 divided by delta z square fijk equal to 0. Yeah. So this is the basic form of the discretized equation. So when we are taking only the coefficients, that is 1 by delta x square plus 1 by delta x square. So what was the question was, in coefficient matrix, what percentage of number of rows will have the diagonal element to be equal in magnitude to the sum of the magnitudes of the off diagonal elements. So if we see that it is 2 magnitude, it is 2 1 by delta x square plus 1 by delta y square plus 1 by delta z square. So in the discretized equation itself, we have the 1 by 2 1 by delta x square, I mean 1 by delta x square one coefficient, another 1 by delta x square, and 1 by delta y square 1 by delta y square 2 1 by delta y square we have here, and 1 by delta z square and 1 by delta z square. So everything added up together we can get the coefficient matrix when all the elements are present. When this would be happening is when this would happen when all the grid points are present. That would be the case where we have the number of interior grid interior okay, not this, number of interior grids would be as we saw in the last one, it is 40 minus 3 into 30 minus 3 into 25 minus 3, which was giving an answer as 40 37 into 27 into 22, 21,978. It is 21,978. So the answer is this many grid points would give us the values. So when we are dealing with this, it is 21,978 divided by total number of rows, that is 27,114. Equations we need to solve, right? So the answer is 21,978 divided by 27,144. It was giving a okay. Once again, just a small confusion. In so doing this calculation, it would come as around like 90% should be the answer. Some calculation went wrong here, so it is coming as 80%. So I'll just recheck this at the end of the session. So the answer to this is actually about 90%. About 90%. So we'll just move to the next problem, that is question 5. Which of the following methods can be used to solve the system of equations Ax is equal to Q described above? So since the system was not a tridiagonal matrix, so the options given for this question is TDMA scheme, that is tridiagonal matrix scheme, Gaussian elimination and LU decomposition. We could not see formation of any proper diagonal elements in the given above method. So TDMA scheme cannot be used. Other than that, Gaussian elimination and LU decomposition, both the methods can be used. So the answer to this problem is second and third. 2 and 3 both can be used. TDMA, because it did not form any sort of diagonal structure, we could not use the TDMA scheme. Next question. Diagonal dominance condition is required for which of the following methods? Gauss-Seidel, LU decomposition, TDMA. That is tridiagonal matrix. So when we are dealing with the iterative methods like Gauss-Seidel and the tridiagonal matrix schemes, diagonal dominance condition is very much required. Whereas in LU decomposition, we are just splitting the matrix and solving it in back substitution. So the diagonal dominance is not very required in the LU decomposition scheme. Whereas when we are dealing with the Gauss-Seidel and TDMA method, we need the diagonal dominance condition to be satisfied for sure. So the answer is 1 and 3, that is Gauss-Seidel and the TDMA. Both of these methods require the diagonal dominance condition. Next we have, you wish to solve the, one second, you wish to solve the set of equations Ax is equal to Q using the Jacobi method. Which of the following conditions must be satisfied by the coefficient matrix for the method to work? It is matrix A is non-singular, matrix A is irreducible, matrix A is not diagonally dominant. So the question was, you wish to solve the set of equations Ax is equal to Q using the Jacobi method. When we are dealing with the Jacobi method, we expect certain criteria, which are the matrix to be non-singular and it should be irreducible and it should be diagonally dominant. Because we are dealing with an iterative procedure, all these three criteria should be working or should be satisfied for the method to work. So when we are dealing with the set of equations to be solved for Ax is equal to Q using Jacobi method, the method demands the matrix coefficient matrix A to be non singular, irreducible and diagonally dominant. All three conditions needs to be met to the see the solution by using Jacobi method. So the answer is 1, 2 and 3. That is fourth option. All three statements needs to be satisfied. Now we'll move on to question 8. The norm of the residual at the end of m iterations can be evaluated as the largest value in the magnitude of b minus axm, and it is norm is b minus axm at 2 and xm minus xm minus 1 2 twice. So the norm of the residual is basically calculated using first and second option, that is we calculate norm as we calculate the residual through this approach. Like, what is residual is that So we are consider the matrix, we are solving it as Ax is equal to B, right? So for let it be for kth iteration x k is equal to bk. So residual is given by b minus bk, that is here b is b minus axk. For kth iteration this is the k, but for mth iteration it can be b minus axm, I mean axm, rather than k we can substitute it as m. So the answer is, when we, this is the formula for residual. Residual is given by b minus ax at power m, I mean mth iteration, that is not power, that is at mth iteration. So the answer is, the norm of the residual is, so the largest value in the magnitude of b minus axm or the b minus axm2. So the answer is both 1 and 2 are used to evaluate the norm of the residual at the end of m iterations. So question 9, it is asking for which of the following is admissible as a stopping criteria with successful solution as an iterative method Ax is equal to Q. When we are dealing with the iterative methods for solution of a CFD problem, we want the residual uh, to approach 0. I mean basically it should be less than a certain value. And therefore the answer is residual less than a limit. The options, first the options given for this problem are the number of iterations greater than a limit, and x at kth iteration minus x at k minus 1th iteration less than a lower limit for all variables, and residual less than a limit. So basically what we do is we go for residual less than a limit, because this would be easier to keep track or keep check when we are dealing with the CFD problems. So for example, residual in the previous slide itself we saw the residual at the kth iteration is given by b minus b at the kth iteration, which should be b minus a at k ax at kth iteration. For example, residual at the 0th iteration would be del dot 0, right? B minus a x at 0th iteration, and at kth iteration it is given by this. So what we want is, we want the delta k to be decreasing. Therefore del naught by delta k should be some, I mean it should be greater than 10 power 3 or 10 power 4. I mean in this range we want it to be happening. If it is in this range, the delta k is decreasing, so residual would be coming below a certain limit. So the answer to this problem is question 9. The answer is option 3, that is residual less than a limit is the right answer for having a stopping criteria when we are dealing with the iterative procedure, like for solving Ax is equal to Q. Now we'll move on to the last question for today's session. Which of the following statements is true about solution of the linear algebraic system of algebraic equations Ax is equal to B with known coefficients? So we have two methods like iterative method and non-iterative method. In iterative method, we have things like Gauss-Seidel, Jacobi, and dry diagonal matrix method, algorithm, everything. And in non-iterative method, we have Gauss elimination and some straightforward techniques like LU decomposition, everything, right? So the question was asking like which of the statements is true about the solution of the linear system of algebraic equations with known coefficients. If Gauss elimination works, then LU decomposition can also be used. Since both of these are non-iterative technique, we can use both. Like if Gauss elimination works, we can say that LU decomposition would also be working. Since both are straightforward technique, the first statement is therefore true. If Gauss-Seidel works, then tridiagonal matrix algorithm method can also be used. This is a false statement because Gauss-Seidel can be used for is an iterative technique that can be used for any matrix A, but tridiagonal matrix requires a certain matrix structure to be maintained, like tridiagonal, pentadiagonal, or any matrix structure to be maintained for it to work. So we can't. This is a limited case. Tridiagonal matrix is a limited. It can be used only for limited certain cases. Only permits use of tridiagonal matrix with those matrix structure, whereas Gauss-Seidel can be used for any of the methods. I mean, it can, if Gauss-Seidel is working, we cannot say or we cannot assume for the tridiagonal matrix algorithm to also work, because tridiagonal matrix algorithm works only for a certain case, whereas Gauss-Seidel can be used for any structure with certain other conditions that are common for both. So if Gauss-Seidel works, it does not mean that tridiagonal matrix algorithm should also work. So the answer to this problem is, if Gauss elimination works, LU decomposition can be used. But if Gauss-Seidel works, I mean Gauss elimination works, LU decomposition can be used. But if Gauss-Seidel works, it does not require for the TDMA to work. So the answer to this problem is option 1. That is only statement 1 is right. So yeah, these are all the problems for today's sessions. If any one of you have any doubt, please feel free to ask. So yeah, before closing the session, we'll just solve the some criteria difficulty that arose when we were dealing with this problem. So basically it would be 40. What was question? Basically, basically what is happening is we are leaving out a few equations. That is my observation. 25 minus 1 plus 40 minus 1 is 39 plus 29, 92 into 2 plus 4 plus 4 plus 24 72. So the first one, number of equations to be solved is true, 39 into 29 into 24. Number of interior grid points would be, we are leaving out 1, 2, 3, 4, 5 and 6. 6 walls we are leaving out. 1, 2, 3, 4, 5 and 6. Yeah, that is also true. Okay. The number of grid points. Okay, actually this would be 24. What do we mean? It's like in the top and the bottom wall, it would be 25 cross. Okay, if we are taking it like this, 1, 2, 3, 4. It is okay. Left and right, we are having 30, 25. What is the question basically? 40, 30 and 25. So it is 40 and 30 into 25. So this is 40 into 30. Again this would be 25 in the sense top and bottom. Okay, if we take it like this, it would be 40 minus 1 into 30 minus 1 into 6 into 2. And left and right wall, it would be 20, 30, 25. 30 minus 1 into 25 minus 1 into 6 into 2. Here again it would be 40 minus 1 and 25 minus 1. 25 minus 1 into 6 into 2. So basically it is like 39 into 29 into 12, 13572 into 29 into 24 into 12, 8352. 40 minus 1 into 25 minus 24 into 12, 936 equal to 936. So it is 13572 plus 8352 plus 936 divided by 12, 1905 plus again now we have like we have taken the interior most points, right? So the next layer also we have taken. So this layer, it is like we have taken all the points Okay. It is not like 1905 into 2 plus 24472 minus 24472 plus 21978. So yeah, sorry for the confusion. We'll just start with a simple 3D case and we'll proceed. We have three 3D and we have 1, 2 and 2. We have 2 and okay. 1, 2. One, two, okay, 2 into 2 into 2. This 1 into 1 into 1. Number of grid points is 1. Forty into 30 into 25 is 30,000. Total grid points is equal to 40 into is equal to 30,000. Boundary points. If we take boundary points, that would be in this it would be 40 cross 30 into 2 again it would be 25 into 30, so it would be 23 into 28 into 2 and looking at this left turn. Okay, 30 அது வந்து 23 இது வந்து 25 into 28 இது வந்து 23 into 38, so it will be 40 into 30 plus 25 into 28 plus 23 into 38. into 2 minus 30,000. So actually here a small confusion went. It is 5548, and so it is number of equations. Actually, the point to be noted over here is the calculations are are approximate as certain points are repeated. So to avoid that, it will be 40 minus 130 minus 1 into, it will be like 25 minus, it will be 30 minus 3, and 40 minus 1 into 29 plus 27 into 24 plus 20 37 into 22 into 2 plus 21,978 39 into 29 into 12 13,572. 27 into 24 into 12 7776 7776 40 minus 3 into 22 into 12 9768. Uh, 20 percentage plus 60. So yeah, this sum is solved, and one more remaining one is 27,000, and it is 90,000. So basically it is sum of what percentage of number of rows will have diagonal element to be equal in magnitude to the sum of magnitudes of the off diagonal elements are. So the answer is, we would be having it in the interior most points. So it is 40 minus we should be having it is 29 minus, what is the question, number of percentage of number of rows will have the diagonal element to be equal in magnitude to the sum equal in magnitude to the sum of magnitudes of the off diagonal elements. 1 by, we will have everywhere 2, and if it is not there, we would be having it as, if 1 is not there, it is not less than 75 percentage. So the answer is coming as 80.81 percentage, 0.81. So it is 81 percentage. So it is, we are approximating it as 90 percentage, and we are solving this. So that's it for today's session. If there is any changes in this practical sums, I will post it updated in the PDF before uploading. So yeah, thank you for today's watching today's session. We'll close today's session. If there is any changes in any of the problems, I'll upload it in the PDF version, update it in the PDF version and before uploading. So thanks everyone. We'll just stop today's. Yeah, thank you everyone. We'll again meet it in the next week, the same timing. Thank you.